Welcome back, everyone, to the eCoreAcademy e-learning platform. My name is AJay Raj, and I'm going to be coming back with you all for another Algebra 1 video, an all-new Algebra 1 video, and this topic is going to be all about regular and compound inequalities. Now, you've noticed that Tanya actually started the course herself. She did her introduction video, and she started off her first unit and chapter. However, Tanya and I will both be splitting up Algebra 1 together, so what we're going to do is we're going to be doing alternating chapters within this Algebra 1 course. If you want to get reference to what exactly those chapters are, I'll also tell you before each video what chapter each video is within, but it'll also be organized on YouTube together collectively, and it's also available on our website at eCoreAcademy.org to see the structure of each and every single one of the units and where each lesson would go in order. But I'll be starting off with our second chapter within the Algebra 1 course, which is all about absolute value inequalities. Now, before we get into the more complicated steps of the absolute value inequalities, we're first going to take a look at the background of inequalities, some regular and compound inequalities. This is something that should be a review from pre-algebra, but then we'll start to introduce to you the compound inequalities and do some heavier practice. But before we jump into today's lesson, please make sure to do 4 things. Please make sure to smash that subscribe button, hit that like button on this video, turn on post notifications by clicking that bell icon right next to that subscribe button, and feel free to drop a comment down below. Also, as an extra added fifth measure, please make sure to share that video either through YouTube or any other social medias, such as through our very own social media accounts as well. As I was saying, we're going to be discovering the algebraic representation, formatting, and problem solving of compound and regular inequalities. We'll be taking that recap from pre-algebra, and then we'll start to advance those methods. So without further ado, let's jump right into it. Let's start off by taking a brief overview of what exactly these inequalities are. So what exactly are inequalities? What is their representation in Algebra 1 or in algebra alike? And what exactly do they entail? How do they help us? So inequalities are a comparison between values or data sets. You're merely comparing different values to identify whether or not one is greater than the other, whether or not they're equal, they're non-equal, or whether or not a certain value can fit within a given data set. And specifically, a compound inequality involves multiple sequences of valid data points on a number line by joining multiple inequalities with either and or. So this has to do with multiple sequences of basically 2 or more inequalities given. In this case, we're going to be focusing on 2 inequalities for these compound inequalities when these 2 inequalities are essentially joined together on the same number line. What exactly do they represent? Will they coincide? Do they have definitive endpoints? Or are they completely 2 separate inequalities? And we'll show you how exactly they might compare. And inequalities are useful in real life when you're giving information about unknown variables. When you have absolutely no idea about the variable, you can still give a distinct value of integers that can suffice for that variable. And this has to do with your graphs on your coordinate planes. So if you were given a variable such as x and you were saying that x was less than a certain value in just layman's terms, x can be less than, say for example, x is less than 3. If you're saying it in English, what that means is you can have any value below 3 that is valid for that given set of data points. And this helps you with the coordinate plane when you're trying to find restrictions on your graph, whether or not a certain graph can fit in a certain area, whether or not a certain x value is going to be utilized within the coordinate plane itself. And I'll also get into that in a deeper measure when we go into our absolute value inequalities, how exactly this relates to graphs like your absolute value. And later on, I'll introduce that in parabolas. Tanya and I will both be introducing that. And the number one key to actually represent your inequalities, it's more than just writing it in written format. And algebra, I'll also show you that representation. That is very important. But one main way, probably the most popular way, is to graph everything. Algebra is all about graphing, whether or not it's the coordinate plane or the number line. The number line is merely a counterpart of the coordinate plane, if you think about it. The coordinate plane is just 2 number lines intersecting with each other to make coordinates. So as you guessed, this whole lesson is going to be revolved around the number line. I'm going to be showing you how to signal and signify these inequalities on the number line, showing infinite values, included values, excluded values, and extensively so on and so forth. So let's make sure that you guys are tuned in. You have your listening ears on. So we're going to start with our basic inequalities, and then we'll start to move on to our compound inequalities. Then I'll introduce a word problem and a special property at the end. So stay in tune. Let's move on. Firstly, let's start off with equal and unequal values. Very simple enough. We're going to be identifying whether two values on either side of your inequality sign, specifically your equal and unequal value signs, whether or not they're going to be equal and how exactly to represent that. So, unequal and equal formatting on both a graph and also algebraic representation visually. So equal values are variables or representative values that hold the same numerical equivalence. The reason why I said representative values is because you're not going to be given necessarily two numbers that are equal to each other. Tanya will be covering that in her types of solutions video. That's when two integers are equal to each other. That means you're going to have infinite solutions. In this case, we're going to merely have a variable and then an integer, meaning x can either, let's say for example, we'll utilize x here, x can be equivalent to 3. So we're going to be utilizing variables and we're going to be assigning them integer values or an equation on the other side that's equal to x. And how exactly would you represent that on a graph? Well, we know that x is equal to 3. That means x holds the same value as 3. Therefore, we're merely going to be plotting a 3 because that's the only valid point within this equation itself that will be represented on the number line. Now for our unequal values, these are variables of representative values that do not hold the same numerical equivalence, meaning they're not equal. And because we're seeing here, that's how you write the unequal sign. You're merely writing a cross or a slash mark through the actual equal sign to show that it's not equal or cannot equal. So x cannot equal 3 or does not equal 3. That means there are no value points that we know of that is equal to x. Therefore, we would be leaving a blank graph, because there are no valid points that we know or we can derive from this equation here. So that would be a blank graph. Now, moving on to our less than inequalities. These are inequalities that show whether or not how exactly one value is less than another and how to represent that and how exactly you'd graph that. So there's two possibilities for less than inequalities. You can have a value that is less than another value. You can have a value that is less than or equal to, and I'll show you exactly how that formats. So for our less than inequalities, this occurs when the value indicated to the left is less than the corresponding value to its right. That means all of the possible data points on the left side, meaning the variable itself, must be less than that value and cannot be equal to it. So for example, this is how you'd represent it. X is less than 8. You would show that little opening mark, that less than sign. It would be facing away from your left-hand value, your X, and it would be facing towards the right-hand side. Whenever it's facing away from your variable, the variable of focus, that means it's less than. And it's always in relation to the variable on the left-hand side or the integer on the left-hand side. So x is less than 8. It can be anything from 7 on downwards, and it cannot be equal to 8 in terms of integers, but it's everything below 8. Now, how would we represent that on a number line? Well, we know that we want to include all the possible values that are less than 8. That can be all the way up to your, your closest integers, like 7.99999. That's an infinite, that's a non-terminating decimal, essentially. That's going to go on forever, and we cannot show that on a number line clearly enough. So what we would do is we'd utilize our known integer of 8, but what we would do is we'd put an open circle around the 8 itself. So we put an open circle around 8. The reason why we're putting an open circle around 8 is we're showing that it's not including 8, but it's everything less than 8. So we'll start to draw that line going towards the left with that line. It's going in an infinite manner. Sorry about that. So it's going infinitely towards the left. Just like that. That's our representation right there. Now for our less than or equal to values, it's when the value indicated to the left is either equal to the value on the right or smaller. So it can not only be less than, but it can also be equal to. So in this case, it could be a value like x is less than or equal to 8. You would have that less than sign, but you'd also have that small line at the bottom that's representing less than or equal to. So how exactly would we represent that? Instead of putting an opening circle, we'd put a closed circle on 8, and then we'd start to etch out our line going towards the left because it's less than. And I wanted to draw my number line a little bit above the number. I'll draw my line a little bit above the number line so you can actually see it and it's not straining your eyes. But that's the basic example here. The main difference is that everything's going to be going towards the left whenever it's less than, all the values towards the left of that number, because you're decreasing when you're going to the left going leftwards on the number line. But the only difference is that whether or not the value given is going to be included or excluded. If it's equal to, less than or equal to, it's included. If it's less than, it's not. We're going to be moving on to our greater than inequalities. These inequalities have the same exact genetic makeup as our less than inequalities. However, the only difference is that the sign is merely flipped. So it's going to have the excluded, included, greater than or equal to, and greater than. Same exact properties, except that the sign is going to be flipped. So we're going to take a look at the greater than and the greater than or equal to statements. For our greater than statements, we have whenever the value indicated to the left of the sign is greater than the corresponding value to its right. Like I said, it's always in terms of the left-hand side value or variable. So as you can see here, x is greater than 5. The mouth is going to be facing towards x, showing that it's greater than 5 and it's not included. 5 is not included in this data set. So how exactly do we represent that? We're going to put an open circle here on 5 because it's excluded. And then we're going to draw our line going towards the right-hand side, as so. So it's going to be moving towards the right, like I said before. Less than, you're going towards left. Greater than, you're going towards the right. Increasing values go towards the rightwards. And then, of course, 5 will not be included in this data set because it's only greater than. Now, for greater than or equal to, it's when the value indicated to the left is either equal to the value on the right or greater. So how would we represent that? That could be represented, for example, as x is greater than or equal to 5. This merely means that 5 is also included in this data set, and it's everything greater than or equal to 5, so it's moving towards the right. So we'll have a closed point here, and then we're merely moving onwards towards the right-hand side. Just bold that for you guys so you can see. All right, now we have finished our greater than or equal to, less than or equal to, and less than, greater than or equal to, greater than, and also our unequal and equal. Now is the fun part. Now we get to move on to our compound inequalities, and this is compound inequalities part 1. So we're going to start off with our and compound inequalities. This is our first type. There's 2 types, and and or. We'll start off with our and. So the and statement, or the and compound inequality, occurs when the solutions of 2 given inequalities are the only included solutions that also coincide. This occurs when you have 2 different inequalities represented on a number line, and in between those inequalities, all you're going to have is the word and. Now, what exactly does that mean? That means that both of those integers, both of those inequalities, they will both pass as the same exact set of data points on your on your number line. And instead of going on infinitely in either direction, it's going to have a definitive endpoint. So you're going to have definitive endpoints like a line segment. You'll know exactly what your values are and how many values you have. So, for example, if we're given the inequality x is greater than or equal to 2 and x is less than 6, it's conjoined by the word and. That means they also coincide with each other. So that means we can rewrite it as 2 is less than or equal to x and is less than 6 because they are both on the same number line representing the same data points. Now, let me try and explain this differently. So say, for example, you have your value of 2, right? We know that x can be greater than or equal to 2. That means 2 must be less than or equal to x, which means that 2 and anything up is going to be valid for x. However, we also have another restriction. X is less than 6. That means that x must also be greater than or equal to 2. It can be greater than or equal to 2, but it must end by 6. That has to be less than 6. So how exactly would we represent that on a number line? Well, let's start off with our lowest value. We have 2 right here. If x is greater than or equal to 2, that means we're going to put a closed point on 2. And it's going to go on infinitely towards the right. However, we know that x must also be less than 6. Because of that less than 6, we're going to have a line segment between 2 and 6. And because it's not less than or equal to, we're going to put an open point at 6. Now, because both of these restrictions pass, it's essentially the crossing point of both inequalities. So because they both have this common set between 2 and 6, we're merely going to connect those points to make our line segment. Now, if you were to think about this in a graphically, how exactly this would work, let's draw out our actual inequality here. X is greater than or equal to 2. So let's erase this here. So we have x is greater than or equal to 2. That means all of the values greater than 2 are going to be valid for that specific inequality. However, we're going to be passing on another restriction, which means that all values must also be less than 6. So we're going to put an open circle at 6, and essentially all these values, let me just heighten this up here, all these values must be less than 6 as well, right? Now, the only way that both of these inequalities will work is if this set of value points work, because this is the intersection of both inequalities. That's all your AND statement is. It's when both inequalities intersect. Therefore, your inequality would merely remain as your AND statement, 2 is less than or equal to x, which is less than or equal to 6. All valid points. All right, now let's move on to our second type of compound inequality. We have our OR compound inequalities. So your OR statement occurs when the solutions of two given inequalities are the only included solutions that don't coincide. So merely it's two inequalities, except that these inequalities instead do not intersect each other, but they go in opposite directions. So it's because they do not intersect each other, that means whatever your integer is, it's going to be in either one of the data sets, and it won't be in both data sets. So because there is no intersection, your integer or your variable will be in either one. I'll show you exactly what that looks like. So the way that we signal this is with an OR in between two different inequalities. So for example, we have x is less than or equal to 3, or x is greater than 5. You can notice that there isn't going to be any intersection of these inequalities. They're actually going to both go in opposite directions. So that means your value cannot be any of the in-between values in between 3 and 5, and they must only be in one of the data sets. There's no way they can be in both. So how would you rewrite that? Well, just to say this up front, like our AND statement, we could rewrite it and simplify it. If this were x is greater than or equal to 3 and less than 5, then we can merely write it as 3 is less than or equal to x is less than 5. However, because they're not a part of the same set, they're part of two separate sets, it cannot be formatted differently because it's not a fluid set of data points. So that's the simplest way to write it. Now, graphically, how exactly would you represent that? Well, you can just think of it as two separate inequalities that you're graphing. So we have x is less than or equal to 3, so we're going to circle x right here, and then we're going to move onwards towards the left. We're going to move on towards the left. Write that a little bit thicker. So x is going onwards towards the left because it's decreasing. It's less than or equal to, x is less than or equal to 3. Sorry, we're going to put a close point. I apologize. I'm going to put a close point at 3. Move this onward to the left. And then for x is greater than 5, we're merely going to put an open circle at 5. And then we're going to increase infinitely towards the right because it's increasing in that manner. So these are two separate data points. Everything in between here, everything right here, not valid, including 5. So everything right here in this whole blur between 3 and 5, including 5, they're not valid points. And everything onwards would work, essentially. That's the whole point of it. So anything in between would not be valid, and your integer x would either be in one or the other inequality to actually work. All right, now let's use a word problem. Simply enough, those compound inequalities shouldn't be too difficult. Just doing some practice is useful, so that's why I'm going to be introducing this word problem to you. So this is a department store word problem, just to give you some background. So at a department store, Jason's allowance permits him to buy up to $20 worth of juice boxes. They're worth $1 each, granola bars, which are $2 each. Set up inequality to represent valid amounts of each item that he can purchase. So what is the maximum amount of each value that you can actually purchase? Now, we know that you cannot purchase a negative amount of objects. So within a grocery store, you can't really, any realistic object you cannot have a negative amount of other than money itself. So in this case, for an object itself, we're not going to include any values less than 0. So we don't have to include that in our inequality unless otherwise specified. So we're going to determine whether or not we're using an and or. But in this case, we are going to be using an and statement, because the reason being is because when you're buying a juice box or you're buying granola bars, that value is going to be added together. So it's going to be coinciding value. So it's going to be an and. So using these variables, J being juice boxes and G being your granola bars, we're going to figure out our equation. And our equation is that J must be less than or equal to 20 and G must be less than or equal to 10. So the reason being is that J cannot be over 20, and because it's $1 each for each amount of juice box, each juice box. So you can have a maximum of $20. Therefore, it's going to be less than or equal to 20 because you cannot surpass 20. And G must be less than or equal to 10 if you're if you're looking for a maximum amount. So G is less than or equal to 10. It can equal 10 when J equals 0. But in this case, you cannot have more than $20. Therefore, because granola bars are $2 each, you can have a maximum of 10. So this is a quick example of a word problem. Now, finally, for our last slide, we're going to be looking at the properties of negative. This is a special property that I just wanted to throw out there. You can solve inequalities like equations, so you don't just have to have a variable and then an integer on both sides. You can have equations, and you can solve them like equations as long as the comparison is still available. However, the only difference to an equation is that whenever you multiply or divide both sides by a negative, you must flip the direction of the sign, the inequality sign, unless it's an equal or non-equal sign. So for our example, we have, as an example, we can utilize 2x minus 3 is greater than or equal to x in this manner. So if we want to solve for x, what we can do is we can subtract 2x from both sides to isolate your variable. We're going to get negative 3 is greater than or equal to negative x. And in this case, you want to figure out what x is and not the opposite of x. So you'd be dividing by both sides, or you can multiply, but I would divide in this case just to not make it confusing. So you divide both sides by negative 1. Because you are dividing by a negative, dividing by negative, you would have to flip the sign. So that means 3 is less than or equal to x. That's all you're doing. You're just merely flipping that sign. Whenever you multiply or divide both sides by a negative, whether or not you're fully simplified or not, whenever you do that, you must flip the sign. So in this case, 3 would be less than or equal to x. And it does show the exact same value when you graph it on a number line. All right, everyone. So that'll be it for today's video. I hope you all enjoyed. This has been AJ at the eCoreAcademy e-learning platform. Please make sure to like and subscribe down below. Turn on post notifications. Check out our website at www.ecoreacademy.org. Visit all of our socials at Pinterest, Facebook, Twitter, Instagram, and TikTok. And utilize social media platforms to share all of our videos. Once again, everyone, I hope you all enjoyed this video, and I'll see you all in the next one. Peace.